Hi, I'm Max Schettler, and today I'd like to talk to you about the work I did together with Dominik Buse, Anatoly Zuboff, and Falco Dressler here at the Technical University of Berlin on how to train your intelligent transportation system. That is, how we integrated machine learning with vehicular network simulation. So, looking at this, let's first consider an example problem that we could face in intelligent transportation system. So, in this case, we have two vehicles on a serpentine road where the following vehicle tries to communicate information to the leading vehicle. To do this, it has multiple options. It uses heterogeneous communication, so it can choose to transmit information via DSRC, which is very reliable, but also has a large interference domain, or via its VLC-enabled lighting modules, which are more situational. For example, they won't work in the curves because the leading vehicle is not illuminated in those. So it has to make this decision, and to define an optimal choice between those, you could now start implementing an algorithm. So you would set up a simulation and you would try to optimize for that. But if we look at this more formally, we can observe that we actually can decompose both. So we have the scenario on the left and we have the solution or the solution attempt on the right. If we treat it like that, then we have to consider how our solution attempt actually works. So what is its input and what is its output? So the input might be, in this case, the receiver position, because this is where we want to go, and that's the most influential characteristic for visible light communication. And the output then will be what communication methods should be chosen. And at a later point, then we would like to know whether that was actually successful, because in this iterative process, we will need to see whether our communication is successful, so we can compare different approaches that we take and try to come to an optimal solution. If we look at this as from a more abstract perspective, though, this starts to look a lot like reinforcement learning problems usually are formulated. So the left scenario is our environment in this case. The solution attempt is the agent. The receiver position is the observation that the agent knows about. It can influence the environment via the action that it's choosing. And afterwards, it's notified about a reward, whether the action that was taken was desirable or whether it was not desirable. And if we want to implement it in such a way, we need to start first implementing the environment and the agent. So for the environment, that is pretty straightforward for us because we can use our usual tools. In our case, this was the Zumo for traffic simulation. We used Veins for the communication part and the extended Veins VLC to implement visible light communication so that we have two different communication methods. On the agent side, we use tools that we are not so familiar with. So we use TensorFlow, but you could also use PyTorch. These are the two large machine learning frameworks that are commonly used. You could also start looking into using algorithms from the literature that you find interesting or optimization problem solvers. But what you start noticing is that there's a barrier in between. So these the solution side and the scenario side speaks different languages. That might be different programming languages, but we also need to decide what is the actual input information and how do we encode this such that the machine learning framework, for example, can use it, and how do we use the output of this framework in our simulation to make the actual decision or to influence the simulation. So we need to have some form of translation in the middle between the environment and the agent. And this is what we implemented in our paper. We implemented VeinsGym, which is based on the popular OpenAI Gym concept. And for input and for output, we do some translation here. For input, this means that we consider the receiver position and the reception success as observation and reward. And the position is encoded as 4 floats, that is 2 floats for the relative position of the vehicles and a unit vector describing the rotation of the receiving vehicle, as well as a reward for the reception success, which is a number between 0 and 1. The outcome is a number between 0 and 7, in this case 110, which can be considered as a bit vector for each of the transmission methods that we have. So it is regarding DSRC and the headlight and the tail light. So this component in the middle enables implementing this, and actually it's pretty straightforward. So if you're interested in this, please check out the software at the URL shown on the screen. So what does this mean for me if I want to apply VeinsGym now to my own research? So I have this project and I might have a problem that I already implemented somewhere or that I have in my mind to consider next. And what now is different when using VeinsGym, I need to make it more formal. I need to follow some pattern. I need to define where actually is the interaction with VeinsGym. So when do I need input from a solution? How does this input look like? So what is an action in my case actually? And what information might be relevant to this solution? But rather than considering this as overhead, as unnecessary work that I need to do that I wouldn't have to do otherwise, I think that's actually an advantage because this new representation, this formal representation of your problem is human readable, it is shareable. So when I publicly make it available, I can just port it to different platforms. Other people can look at my work and it is reproducible by default. Once I have this, I can then solve it using generic solvers that are readily available on the internet. Actually, for our work, we used TensorFlow and we did not put too much work into this. And it can get even better because in the OpenAI project, for example, there are servers published that can be called just from the command line. So in a best case scenario, you don't even have to write code for your solver, but rather you can apply it to your environment that you defined. And in general, this decoupling from problems and solutions make it possible to think more focused on the problem, to compare among different problems that other people might have stated already, and to work independently on solutions and see how they fare against not only the problem I'm formulating right now, but maybe also related problems from the literature. And this is a great benefit, I think, for VANET research in general. So to conclude this, we think that problem and solution decomposition is easy to use with the VeinsGym. You can, in relatively few steps, apply this to your own ITS challenges that you find interesting, and it is very beneficial to you because we can solve these problems now using automated tools such as reinforcement learning instead of figuring out all the parameters and the behavior that might solve the problems on our own. And if this is interesting to you, I invite you to come have a look at our paper, which is shown here on the screen, and to also have a look at our code, which you can find on the internet available. And with that, I'd like to thank you for your attention, and I'm looking forward to your questions in the discussion session.